welcome one of our colleagues from MSR Cambridge, Tim Harris, who just joined this summer from the University of Cambridge. Tim has worked on a lot of interesting language work, both at Cambridge and now at the Microsoft Research, and he's going to be talking to us today about leaky regions. So, an intriguing title. So, Tim.
Thank you.
And the other thing is, Tim will be here for today and about half of tomorrow. And if you want to talk to him, he's just sitting in Tom Ball's office. So I haven't set up a schedule. You can just send a mail or come by and find him.
Okay, good morning. So what I'm going to be talking about is one of the things I've done since joining MSR Cambridge. The other thing is some work on software transactional memory in Haskell, and I'll probably be doing a talk on that on Thursday. So come along to that too if you're interested.
Isn't that down in Mountain View though?
No, this is to the big top people.
Oh, okay.
So this was really some work I did as a way of getting up to speed on the Bartok compiler. As I go through this work, you'll spot probably two things that make it perhaps somewhat specific to that setting, or at least difficult or more costly to apply in general. So I still need to do some thinking about whether this really works as a good scheme, but hopefully some of the numbers about the memory aspects of this will be interesting nonetheless. So the starting point for this is a hypothesis I've had for a while, which is that if you take a program that's managed by a garbage collector and stare at it really hard, you can probably point to places in the program where it would be safe to free the objects that the program has allocated. So the garbage collector, of course, automates that by perhaps tracing over all the reachable objects and deallocating them that aren't reachable. But probably a smart programmer could put in free statements. Now, the garbage collector, of course, is getting lots of advantages. There's the standard ones that it makes allocation fast if it can just bump up an allocation pointer. There's the fact that we don't have to worry about the same kinds of crashes, of course. But in the case of just trying to work out where to put freeing statements, we also get an advantage that the garbage collector means we don't have to we don't have to do that in the base context that, say, a library is being used. The decision of where to free objects might depend a lot on the whole program, rather than being a decision that can be taken locally by the writer of some code. So as a way of seeing why or whether this hypothesis does hold, I start off by thinking about one particular case of this that came up on one of the singularity discussion lists. I think it was a point that came up when talking about the interaction between scheduling and the garbage collector, which is if we had some kind of periodic task that perhaps is doing something like decoding a frame of video, then it would seem to be the case that the objects allocated while decoding one of the frames are probably going to be garbage by the time that that frame has been finished. So a kind of stylized version of that code would have a loop, some kind of begin task, some time-sensitive work decoding a frame, and then at the end of the task, a blocking operation to wait for the next frame. And so if we could identify blocks of code like this, where the objects allocated within the block are garbage at the end, then perhaps we can have an implementation mechanism that allows them to be reclaimed immediately we get to the end of that block, rather than waiting until the garbage collector happens to run. Because it would be nice if the GC work here could be done at this point at the end, when we're waiting for the time for the next frame to be decoded, rather than at a more arbitrary point where the heap happens to fill up, because that might be in the middle during the more time-sensitive portion. So hopefully this is going to, in code that has this kind of structure, provide a way of perhaps reducing the cost of GC, but also of controlling when that work occurs, so the cost can be put somewhere off the critical path. So the basic idea is to annotate methods in a program with an annotation saying that most of the objects allocated within a call to that method are garbage by the time the method finishes. So in the previous case, we'd have to pull out the code for decoding a frame of video, put the annotation on, and then it would satisfy this system. And crucially, unlike most of the related work here, these annotations don't have to be entirely precise. It's going to be safe for objects to leak out of one of these scoped regions, and they'll then be retained in the normal heap. It won't lead to crashes or that kind of problem. So we're going to use runtime checks for violations rather than doing some kind of static checking to prove the correctness of annotations. Poor annotation will lead to poor performance.
Question.
Yeah.
Is it so difficult to determine this without the annotation that you need the annotation? Or why can't this technique just be applied to all methods?
So I've got some stats later on about a kind of instrumentation that considers all methods and gives some numbers about how many times the method's called and the volume of allocation within the method. So the way I've actually put the annotations on in practice is to run that kind of instrumentation and then look for methods in the list that are called reasonably often but not too often and that have a lot of allocation inside them. And in a lot of the cases, it's not entirely automated because I've looked at the names of the methods involved and said, oh yeah, that's computing the next move in the crafty benchmark. It sounds like a good thing to explore. But yeah, I'd expect that some kind of feedback system could automate this. So the general model is we've got the stack containing references into the garbage collected heap. Then when the program makes an invocation on an annotated method, so decoding the next frame of video, the stack locations and the objects allocated within it are distinguished in some way. And so the dark blue ones are the ones in the leaky region. And then when returning from the method, the dark blue objects that have not leaked will be deallocated, but the one that has leaked over on the right is going to be checked for, and that'll be safely retained. Now, in actually implementing this, there are perhaps three main costs to minimize in making it practical. The main one is actually the check of where objects leak. So this is being done by changing the write barrier code. So every time a reference is created between two objects, we're going to do some extra work to work out if it's going to be leaking an object. So making that fast is critical. The second cost is the one associated with entering or leaving one of these scoped regions. And this is something that had to be considered when picking where to annotate. We don't want to annotate a method that's called 12 million times, even if it would actually lead to a lot of reclamation because of the extra cost of entering and leaving. And the final cost is a space-related one. Some of the previous work has used schemes which rely on segregating on pages objects that are in these kind of regions. And so if you have a deeply nested call chain with recursive calls to annotated methods, you end up spending several K per call, and so you perhaps hasten garbage collection rather than providing an alternative. In trying to avoid these costs being too great, the key assumption I've kept is that the checks for leaks are ones that have to be there for safety, but that hopefully are not going to be taken very often. So performance would be poor if annotation wasn't done judiciously.
So the primary advantage you're trying to achieve is performance? Is that right?
I'd say so, yes.
So you're going to have to do better than, you have to be significantly better to pay back for all these costs.
That's right. So there's quite a bit of work doing related things here. The one that inspired the title, of course, is Toff and Tolpin's region-based allocation for originally ML, and the more restrictive form of that that's in real-time Java. And these systems use a model in which the heap is composed of a stack of regions, and all allocation occurs by pushing new regions onto this stack, and then by allocating objects in an appropriate region. And space is deallocated by popping an entire region off this stack and reclaiming all the space the objects in it occupied. So typically these regions would be perhaps invocations of a series of functions, and if the function corresponding with this called the one corresponding with that, then an allocation in here might be allocating the objects that are going to be returned from the function, so that when the called function's region is popped off, the return values are still retained. Now these region-based systems have all used static analysis or checking of annotations of region usage to make sure that the discipline is safe. So the Toft and Tolpin scheme makes sure that you don't dereference pointers that are going to a region that's been deallocated, and the RTSJ scheme makes sure that you don't have pointers that are going effectively upwards in this region stack from an older region to a younger one. So the assignment of allocations to regions has to be done in a way that guarantees safety. There's no way of tolerating occasional leaks. And a kind of intuitive reason of why you might want to tolerate occasional leakage is perhaps the function returns through a normal code path most of the time, 99.9% of it, and everything allocated in it can be reclaimed. But then the other rare time, it returns by throwing an exception, and the memory usage pattern is quite different. So that's maybe an example why you want to have dynamic checks rather than something that's purely done statically. Two other areas of related work. There was a bunch of papers at Uppsala 99 using escape analysis to do on-stack allocation for Java programs. As with the region systems, they had to be proven safe to make sure that stack allocated objects didn't escape from the allocating context. The analysis that was done, I think, in all of these systems was per method. So an object was considered to escape if the calling method might leak it in any way. Whereas a lot of the benefits that I've seen with the benchmarks I've used here actually benefit from having multiple methods considered as the context that things leak from. So it's safe for an object to be used some number of levels back up the call chain, and then it's only at the point that the annotation occurs where it mustn't leak beyond that. So we get to potentially reclaim more early a larger number of objects by considering multiple stack frames. The most directly relevant work was at ISMM 2002, where they had a feedback-directed system where allocation sites were marked as escaping or non-escaping. And then they had a write barrier that tracked when an object escaped, I think again in this case on a per method granularity. And once an object from a given allocation site had escaped, the allocation site was flagged as escaping, and subsequent allocations went in the general heap. The analysis that they did looked purely at the memory-related aspects rather than at overall runtime performance. So I think the paper suggested that they couldn't get the system to run at acceptable speed. So I'll talk a bit now about the implementation that I've done in Bartok, and then go through a number of benchmarks and just say where I put in the allocations and what the impact on performance of those annotations was. Now, you'll realize here one of the limitations of the work, which is that it is entirely looking at single-threaded systems. And it's, I've only had a set of benchmarks which I think are single-threaded, and a lot of the implementation relies on the fact that there is just one thread at a time. So the heap structure has the heap divided up into pages, and for each page a ownership value saying what kind of usage is being made of that page. So the pages at the top have a usage value saying that they belong to the ordinary nursery generation that the garbage collected heap is using. The pages at the bottom are ones that contain objects only allocated within an annotated method, so they have some other value saying that that's what the page contains. And we've got a further ownership value that says that the ownership of a page is mixed, that we've got some objects of different regions on it. And having this is actually important because it means we don't have to leave behind the remainder of the current allocation page when entering an annotated method. In otherwise, there'd be the risk of a lot of internal fragmentation of page fragments that are left. The stack then has extra records on it that correspond to the sites at which annotated methods are called. And they will hold information about the allocation pointer at entry to the annotated method and to how much of the GC write buffer has been used. The write buffer is the simple logging kind, where it contains references to the objects that might potentially contain a reference to a leaked object. And so each time that a store is done to the heap, we have to work out the ownership of the source and destination of the reference, potentially log the source of the reference into the write buffer for checking when leaving the scoped region. It's interesting to notice the consequence of having the write barrier refer to the object that the leak is coming from rather than the object that actually is leaked. Because it means that if an object leaks and then is subsequently unleaked, so a reference to it is put in something and then nulled out again later, then we can still reclaim it. The fact that it was temporarily escaped and then recaptured doesn't matter. And that, in fact, is important in one of the benchmarks where a large number of the objects leak and then are recaptured by the end of the annotated method. A second aspect of the implementation is I reorganized the virtual address space of the process to allow a cheaper form of comparison to be used in the write barrier. And so the structure here puts the permanent long-lived data, the code, static fields and so on at the lowest virtual addresses. Then the garbage collected old space growing upwards from a higher value, and then the young generation and the leaky regions growing up from a higher value still. So it's always going to be safe to create pointers that are going downwards from higher virtual address to a lower one. And that means that we can reduce the number of times that the more expensive code paths in the write barrier are taken. If the reference is going upwards, then we need to go and look at the ownership values, and if it's going downwards, then we need to then we can be certain it's not leaking something. This is the key point where I'm assuming single-threaded applications, because obviously otherwise there'd be an intermingling of things. Yeah.
Do you also assume that you don't have any pinned objects?
Yeah, that's right. So if we're running a program that makes an annotated call, the heap fills up with the objects allocated before the call, the ownership value set to the new generation. Then within the annotated call, the heap continues to be filled with the allocations there, and we get the ownership values for the annotated region and the crossover page. Then when leaving the region, I evacuate the things that have leaked by essentially doing something like a semi-space collector. You copy them once out of the region of the heap that's going to be deallocated, and then copy them again back down to to merge them in with the pre-call objects. And that, although it's got a potentially bad cost if a lot of objects do leak, it hopefully has a low cost in the case of nothing leaking. It's doing work proportional to the amount retained rather than to the amount deallocated, which would be the case with a compacting collector. So if we look now through a set of benchmarks that I've applied this to, the first one is XLisp, so an interpreter that runs a series of Lisp benchmarks. And the table here, I'll zoom into some of the examples in a minute. The table here has, on the left, the method call site, and then columns saying the number of times the call is made and the volume of objects that are allocated within that call. First of all as bytes, and then as a percentage of the total allocation. So at the top, there's a call from one of the constructors to XL load, which corresponds to loading in one of the benchmarks that the Lisp interpreter is running. And so this is called 20 times. It does, I think, just over 2 gigabytes of allocation within those calls. And this is 99% of everything that the process allocates. But this is really not going to be a good place to put an annotation on, because each of those calls, since there's only 20 of them, will be allocating about 100 megabytes. And so there'll be several garbage collections within that unless we size the heap to an extremely large volume. So we need to look for call sites which are called a modest number of times, but that still have a decent amount of allocation under them, in the hope that the call is returned without triggering a garbage collection in the meantime. So another example of one that could be considered is this one is part of the evaluation functions in the Lisp interpreter. It's still got 99% of the allocation under it, but it's called 41 million times. And so if that was annotated, then I don't think it would perform well because of the large number of calls and the housekeeping cost of entering and exiting them. But looking further down, there's a couple of call sites that are more effective. These ones, again, as part of the evaluation functions in the interpreter, have a few million and a few 100,000 invocations, and still have a very high volume of objects allocated within them. So those were the two that I chose to use. And so, you see, it's a kind of semi-automated way of working out where to annotate. I've got a profiling tool that creates this kind of log, and then I have to look down manually and work out some kind of trade-off between the volumes involved and the numbers of invocations. It could potentially be done with some kind of more methodical cost-benefit system, I'd imagine. So these two annotations for XLisp correspond, from the table, to a sizable portion of the allocation. And as you see, there's a very small portion of the objects allocated that leak out of the calls. The ones that do leak permanently are where the Lisp interpreter is allocating new space to the garbage collected heap that it's managing. So some of the benchmarks cause that heap to expand. Wherever the interpreter had got to, then allocate space to the Lisp heap, and then those escape from the methods that did that. Another interesting thing for XLisp is there's a global context value that's stored in the static field in the interpreter. And as the benchmarks that it runs are being evaluated, a lot of objects get linked into that global context, and then that gets nulled out at a later point. So the ability to allow objects to leak and then to be recaptured actually is key to being able to reclaim a lot of the space here. Something you might notice about these figures compared with the previous table are that the volumes of allocation are actually evenly split between the two annotated methods, whereas the previous table had almost all the allocation being attributed to the top one of these two sites. And the reason for doing that is that the actual behavior of the XLisp program leads to recursion between these two methods. And the reclamation here is being charged to the method that's the kind of outermost level of that recursion. So that is one reason why there's something of trial and error of using the profiling tool, because that doesn't consider the recursion involved. The second program I looked at was Crafty, which is a chess-playing benchmark. And looking at its table for invocations, there's fairly clear near the top a operation that's to do with the search for the next move. And it's got a modest number of invocations. Almost all of the allocation of the benchmark happens in it, and a very small amount leaks. Looking in detail at what's happening here is interesting, because the places where objects do leak are not ones that could be identified by using the approach in the ISMM paper of saying that a particular allocation site is escaping or non-escaping. It looks like the leaked objects are ones where the benchmark's computing some series of board positions. It then decides that one of the board positions has been seen before, and that consequently it doesn't need to remember that. And it's to do with working out when there's a stalemate being forced in the game. So we can't actually annotate an allocation site as escaping or non-escaping, but we could explicitly put in freeing operations, I think after the test, of whether the board position is a repetition or not. The final two benchmarks I looked at were a Go game player and a JPEG encoder and decoder. Go, again, had a fairly clear site where there was a small number of invocations with most of the allocation under it. In this case, getting the next move of the game. Almost all the allocation happens under it, and there were no leaks at all. So that would be one case where I think potentially a region-based system with static checking would be as effective. There's simply, I think it's returning integer values indicating the moves rather than any kind of object allocation. The results from Go will show that although I managed to reclaim most of the 709 megs that are allocated, there's little effectiveness if the young generation is small, simply because the volume of allocation within one invocation of get move will trigger a GC in any case. For iJPEG, there's again a site that has most of the allocation in it, this one that deals with executing confession and deconfession. So if we look at some of the results now, first of all, heap usage and then the overall runtime performance. This is showing the number of pages that have been allocated in the case of XLisp. The dark grey line being the system running with garbage collection, and the dark blue line being the system with leaky regions. So in the garbage collected case, the trace shows it filling the young generation, and then almost all of that being reclaimed. The young generation here is, I think, sized at 16 megabytes. And the leaky region system keeps a much smaller footprint with large amounts of reclamation going on as it executes. And then the call down here is corresponding to where a kind of outer level of calls to this annotated method finally returns. So the kind of up and down jiggling that's going on in the upwards portion is some fairly deeply nested calls where a small amount gets reclaimed each time it returns. And then we eventually hit a point where a larger series of calls returns. Looking at some of the runtime performance numbers then, this is for Crafty, the chess-playing benchmark, and a variety of young generation heap sizes, and for each of those a measurement of the amount of time doing storage management operations. And for this it's including the time spent with the housekeeping necessary for leaky regions on scope entry and exit, the time spent actually doing garbage collection, and the time spent clearing memory prior to reuse of it. There's three different bars here. The leftmost is the storage management time using the annotations that I've talked about. The middle one is the original runtime. so without the more complex code in the right barrier. And the right-hand one is an attempt to measure the overhead of having this system available. So it's got the more complex right barrier, but we don't have any annotations in the code, so it's trying to see how much worse things are made by having the system around. And particularly in the smaller heap sizes, we get a big reduction in the time taken for storage management. A lot of these tests go from ones where if you have it tracing the number of GC invocations, you see it scrolling past almost continuously, to having one or two invocations during the lifetime of the program. Towards the right-hand side, though, the original garbage collector wins, and I think that would be expected because you can reduce the garbage collection time by increasing the heap size.
When you say young generation, do you mean is that the nursery then? Is only one young generation or something?
That's right. This is the nursery size.
Did you read the heuristic for triggering heap collection nursery side? So, for example, in Bartok it does a full heap collection every 8 nursery collections. So on the left, you would be doing one every 8 megabytes of allocation.
I think it is the same.
On the right, you'd be doing one every much larger allocation. So the full heap heuristic was the same.
I think that's the case. I'd have to go and check. Yeah. Of course, the reduction there in storage management time doesn't translate into a corresponding change to the full execution time. And this is showing that if you take into account the full run, then it was spending 1 second doing storage management in the original half a second in the new one, and so that's it's just about double percentage figures, I think, change in the very smallest young generation size. I've got more results I can talk about with people later for the benchmarks, but the general trend is the same. The top line here are the total run times. The middle line are the total storage management costs, and the bottom line are the times spent for storage management, but excluding clearing of objects prior to reuse. So in these cases, there's a big reduction in the case where GC was very frequent because the heap was small, and crossover points, well, in the case of XLISP, about 8 megabyte young generation. In iJPEG, about the same. On the far left with Crafty, it becomes effective just to do GC with I think about 2 or 4 megabyte heap.
So one question I have, what did you do about assignments to static objects and things like that?
That's one of the export costs, so the right barrier has to be set to track static.
Okay, so the right barrier intercepts or monitors assignments to static objects also?
Yeah, and assignments that might be to stack locations further up. So some conclusions here. Although I've got the limitations, as I said, about dealing with single-threaded programs and with benefiting from the kind of right barrier that the Bartok already had, at least at the point I started the work. And I think it's the first time this kind of thing has been done with practical runtime costs. And the previous ISMM work seemed very cagey about what the actual performance was. And looking at the details about the allocation behavior of these benchmarks, it seems clear that there's benefit from being able to handle recaptured escaped objects, and for considering multiple method calls rather than just considering single stack frames at a time. Now, picking the boundary on which to consider escapes, that is the methods on which to put annotations, really is key to getting good performance. And it's been something of a black art here, although there's kind of heuristics for suggesting which methods to consider in the trace. And future work, of course, is to maybe think about whether this kind of technique could work with other collectors and with other forms of light barrier, and, of course, the case of multi-threaded benchmarks. I'll stop there and take any questions.
So is it fair to characterize it this way? The way I understand it is that you have a scheme for essentially dynamically adding an extra young generation to the GC scheme, right? And then have a fixed point where you collect that youngest generation, because that's when you end the scope of whatever your leaky regions. Is that sort of a summary?
That's right, although there can be multiple such times in the case of recursion. So I think the ownership number space allows about 15, 1.5.
So one thing that C# has that, for example, Java doesn't have is reference parameters, which allows you to have pointers into locations on the stack. So what you could have in your world is you could have you could start one of your region scopes, and you could pass a parameter to some location that's on the older part of the stack. Is your byte barrier going to catch that? How are you going to determine the age of the stack of any given stack location? Is it before or after you've entered your leaky region scope?
I think the byte barrier, when this is compiled in, will track all writes through reference parameters, and then on leaving the leaky region, it will look at the stack pointer on entry versus the address that's been updated.
Go through the entire byte buffer, so the byte barrier store buffer upon exiting a leaky region?
That's right.
Okay.
So it surprised me that the runtime costs weren't actually higher, because I've been expecting that it would be logging quite a bit, but the common case code that I wrote actually tests whether the amount of byte buffer that's been used has increased or not during the region, and that code was being taken in many cases almost all the time. So perhaps it's specific to these benchmarks, but it was a statistic that surprised me.
Can you expand on the reasons that this is single-threaded and how you can overcome that to use it in a production system which is going to be multi-threaded?
So one reason is the layout of the virtual address space, and the fact that if the space used for young generations and for these regions is just allocated sequentially, then you can check old to young points by comparing the addresses. Whereas if thread heaps were intermingled, then that comparison wouldn't always be effective. Now, I think there's another problem with objects that would leak from a region in one thread to a static, be read by a second thread, and then the static would be nulled out before the region returned. In this case, the leaked object, I think, might be seen as non-leaked, so that wouldn't be safe, although I'd need to think about that a bit more.
How are the annotations surfaced to the program who wants to use this form of cartridge collection?
At the moment, it's passed in as a parameter to Bartok. So the call sites are numbered when running the tracing tool to get details of the allocations, and then those numbers are passed in for the selected ones. I think it would be straightforward to actually have it expressed in the source code as an attribute, but
The method or inside the procedural logic, or where would you recommend having that annotation?
Is it call site specific, or is it for all invocations of particular method?
here was call site specific because it looked easy to put the entry and exit code around a call site rather than around method entry and exit. And I think if the problems with threading could be overcome, that it would be nicer to annotate called methods rather than call sites. And I think in the statistics there weren't methods that were called from different places, and one should be annotated and the other shouldn't.
There were.
There were not.
So you thought about combining this with a static analysis to reduce the overhead of the instrumentation with the monitoring?
And that would certainly be possible. It's not something that I've been wanting to go down the route of. And I think one of the things I've said before that I'm keen to look at is combining some of the software transactions work with Bartok. And I think some of the analysis there might be similar to try and work out things that can't escape from a transaction versus can't escape from a particular method invocation.
It seems to me that combining this with an analysis of things that can't escape, particularly if you have some kind of analysis that works well in setting of not the whole program, would be an interesting topic to investigate.
Right. And I think if the multi-threading problems can be overcome, then that probably is going to add more cost to the write barrier, and therefore more importance to avoiding that.
The cost of the write barrier you're talking about is still not inordinate. I mean, it's a small constant factor. If you were to use the full-blown write barrier that Bartok has, I believe that would suffice for what you need to do. You would need to worry about static objects. That probably need to do something better than we do now. But I don't think the cost would be inordinate. It would be interesting to try it to see what happens. Unless, of course, you've got experiences that the cost was inordinate. So.
Oh, no. It would be easy to see what happens if the barrier is made to take the full code path each time. And there are, I suppose, really two costs. One is the actual working out whether it's a store that needs to be logged, and the other is the space taken up.
Yeah.
I think it's the run next Lisp where where the Lisp heap is expanded. There tend to be large numbers of logged entries that were stores to the same. It was the same thing being logged,
yes.
And so it was the fact that the barrier was filled up, and then that triggered a GC that's one of the costs, rather than the work trying to work out whether to log or not to log.
Yeah.
Any other questions?